Excellent. Welcome, everybody. Just wait a few more moments. We've just got people coming into the room. Good stuff. Hey, thanks so much for being on time, and welcome to the first of 5 sessions in our Knowledge Zone offering for 2024. Last year, our topics in the Knowledge Zone revolved around specific details and product performance, such as the above sheathing ventilation for roofs, the what, the why, and the products to make it work. So today, let's get started. Today's topic, it's a dig into B1 structure and a discussion on how we should build. Today, as the first in the series, B1 structure is going to be presented by Simon Cator, who I'll introduce in a moment. B1 structure is the first in this series because that loosely matches the sequence of building. So structure and stability, including durability. So durability is part 2 in the series. That's in 2 weeks. Then weather tightness elements are added. That's part 3, followed by H1 energy efficiency, which in our discussion will be focused on insulation rather than efficient lighting and other things that are covered in that clause. And finally, by what we've called the naughty child E3 internal moisture. We're going to run that one as a hybrid event that's online as well as in person at our Auckland office and training centre. So during this presentation, we welcome your questions, comments, and even objections. And where possible, we will answer those along the way and in our QA at the end. Please find the chat function on your screen. In the chat box, we will post links to you during the presentation. And if you have a question, please use the question tab. We are offering NZ RAB CPD points, so 10 points for this presentation that we load for you, and 1 LBP point you can claim for yourself through the portal. So during the presentation, we'll have a couple of poll questions that will be answered by 2 of our nationwide team. We have Richard Hollard, who's on screen now. He's also based in Auckland with me and Simon, and Catherine McGregor, who is based in Queenstown.
Oh, yeah.
We'll bring them in to briefly discuss poll questions, and they'll be available too at the end for our Q&A. Right, Simon Cator, he is our regional sales manager, and he covers Auckland and south to the central North Island. He's still waiting for that call from Great Barrier Island for a job site visit. When he's not waiting for that call and working with designers, you'll find him recording podcasts with world leaders in the building materials and performance space, people like Joe Lesterbrick from Canada. This podcast series was launched just last week with a bunch of interesting interviews recorded already. In Simon's spare time, he rides a Kawasaki KLR 650 and he hosts a YouTube channel examining all manner of home automation gadgetry, software, hardware, which gets sent to him from suppliers worldwide for his testing and opinion. He is quite the player, and one day he'll retire on the proceeds from that channel. So, Simon, let's crack open the cornerstone of code clause B1 structure.
Thank you very much, John. Good afternoon, everyone. Now on screen here, you'll see we've got a pretty typical looking 2-story timber framed New Zealand building. We've got some additional load bearing structure offered by the steel lintels, both above the garage on the right-hand side and the ranch side on the left. The interesting question we asked a group from the FTMA on Tuesday this week was, how would you improve this? One person was counting the stud bays in the upper left. Another one was critiquing the number of nogs in the bottom right. Yes, there are 4 rows of nogs across a 2.7 meter stud. But let's get to the topic of B1. Code clause B1 is part of the stability clauses in the New Zealand Building Code. Before we get too far, we need some clarity. Standard NZS 3604 is not the building code, but it's commonly referred to as such. Hey, apprentice, can you grab the building code from the van? The building code sits under the Building Act, and it has a high level objectives with functional and performance requirements. NZS 3604 is an engineering standard for lightweight timber structures. That is one method of meeting the building code. Clause B1 structure. Okay, with that out of the way, let's get into B1 structure for any building. The objective of B1 is that we need to keep the building standing up in order to protect the people living inside it. The functional requirement is to keep it standing up over time during construction, renovation, and the lifetime of the building. The performance requirement is to keep the building standing up while it has to resist imposed loads, which are named in a long list of 18 items. These include standing up under its own weight or self-weight, and then harder things like water loads, wind loads, and seismic loads that it needs to resist. And then crazy hard things like fire, impact, and even explosions. So what's in the image? What are the possible causes of this? Could it be internal moisture, untreated timber, external moisture, lack of paint maintenance perhaps? If you search for leaky building New Zealand, you'll get a whole lot of images like this one, published in 2015. The code clause B2 requires 50-year durability for the framing or the structural layer. If we have a look at this image, we can see a pretty rusty I-beam at the top there, and the timber below that looks like it's ready to fall apart. If you look below that, you can see the aluminium doors or windows, which would give you the idea that this would be a relatively new construction. Now, if you're an engineer watching this, you're probably thinking, well, this is not my problem. I'm here today pointing out that these things are all connected. If we mess up E2, external moisture, or E3, internal moisture, we affect B2 durability, and that then becomes a B1 structural problem. So this is what today's webinar series is all about. It's the effect of changing something in one area and the resulting knock-on effect in other areas. Now, here at Pro Clima, John's come up with a rule called the 1-100 rule. And what it's all about is suggesting that we take a little bit of time, think a little bit more carefully in order to ensure that we do things better and hopefully improve our durability so that our buildings may last 100 years or even longer. Let me give you an example from the design perspective. So we're all being driven towards providing an R6.6 construction value for our roofs with the new H1. So let's imagine what this looks like in a scallion roof. So an R6.6 construction value requires deeper framing, somewhere close to 300 millimeters of fluffy insulation. More framing and more insulation means more cost. But it also changes the speed of the vapor movement through the structure. Taking some time to model the proposed roof thickness will very likely result in a roof thickness built for the climatic conditions and see an energy demand increase for the building and not getting carried away with expensive framing we might not require. An internal frame, like I'll show with the wall, has the benefit including air control with an air tightness layer and vapor control, as is finally being openly promoted in brands details. What we've just connected is B1, B2, E3, and H1 plus the cost. The impact of B1 structure decisions, frame depth, frequency, options of internal or external insulation layers. These have a real effect on heat and moisture movement. So B1 structure affects B2 durability and vice versa. E3 internal moisture affects B2 durability and E3 internal moisture affects H1 energy efficiency. Just like that, those code clauses cannot be treated in isolation. Improving doesn't automatically mean better cost. Better and cheaper is nice, and better cost neutral is good too, if it affects the energy demand for the life of the building. The only way to know this is to model the performance of the building. A reliable way of doing that can be done with a software known as PHPP. It's named Passive House Planning Package and should be used for all of your designs to reliably predict energy demand during the design process. So we've seen a lot of insulation in the roof in the previous slide, but what happens in other areas of the building? The engineer must prioritize keeping the building standing up. Otherwise, they get a slap on the hand. So make sure there's lots of timber. In the images, we see an extraordinary amount of timber. So let's imagine that all the timber in both walls is actually required because they both prop up an elephant enclosure. The problem is that this has got out of hand. This is not me actually critiquing the strength of the wall, but now we're affecting H1 energy efficiency and E3 internal moisture. There's no room left for adequate insulation to avoid those cold spots. Now, it's long been assumed in calculations that the fraction of timber in a wall is supposed to be between 14 and 18% of the wall in a 90mm stud wall on 600 centers. In their study, Beacon Pathway evaluated 47 new build homes and found that the as-built average was around 34% timber in the wall, with a maximum found at 57% timber in one wall. This would mean that instead of an R2 in that wall, where we had 34%, we would only achieve an R6. So increasing the framing content is being driven by the requirements of various regulations, mostly in relations to structure and weather tightness. These include cladding requirements. Here's another example of what the framing. Yes, John?
Yes, Simon, just a quick question on that, or a statement. The QR code, which is on your previous screen, if you want to flick back to that QR code links you directly into the Beacon Pathway article and where those photos are from, and there's some additional information there, additional links out. So those QR codes that'll pop up during our presentation, forgot to mention those at the beginning, but they are direct links that we have chosen to support some of the arguments that we're making. So that's a safe link. I've just checked it actually. I just stuck my phone up and picked that link up. So good stuff.
Fantastic, John. Thank you for that. So here's another example of where the framing has obviously taken precedence over the insulation. So you might want to ask a question, what good is the insulation when it only fills these tiny squares? Now I'm going to hand back to you, John, for the first poll of our webinar today.
Good stuff. Right, this is a really tough one. Well, it's kind of tough. It's a bit of fun, really. So the question that we're asking you, and as you answer this, it's quite straightforward. You click on the box and you need to submit your answer. So the question is, are Nogs or Dwangs, if you're in the South Island, are they required as is written in NZS 3604 2011? So easy, short answers there. Yes, no, I think so. And finally, I thought so up until now. So make your selection on that. And as we do that, we're going to invite our panel to jump in on this. So Catherine and Richard are going to join us to answer this question and give us a bit of clarity on this. So I think let close. Everyone happy on the poll? Okay, so that means that we've got over 60% of the votes already in. And what have we got? No. I love it that 58% of people have no on there, and I love the final two. So thank you for those people who have questioned your thinking right now. So I'll leave it up to the panel to give us a clear answer on this.
That's interesting. What was it? 58%. Sorry, it just disappeared there. 58% say that nogs aren't required, so that you'd assume around 58% of buildings or timber frame buildings don't have nogs. If the designer doesn't think they're needed, then they probably aren't putting them in. But we still are seeing, most timber frame buildings with nogs. But no,
I wonder if it's the builders or architects answering that. I wonder who's
yeah, exactly. We don't know who's answered what. It's all anonymous, but yeah, exactly. I mean, there's been numerous reports and studies done over the years. I know Sean from Oculus did a great article a while back, 2019, I think, listing all the different studies that were done over the years from the 1990s onwards. I think there's 4 or 5 of them. I don't know, maybe we need another 4 or 5 studies just to prove that the studies are correct. But yeah, to show that, hey, you don't need nogs. Sean was pointing out that there are 2 ways of complying with structural requirements, and your cladding can be used basically to keep the timber straight, which is great. And I mean, the advent of kiln dried timber, yeah, it doesn't twist and turn like the old timber used to. Anything to add to that, Kat?
Yeah, I guess there's other forms of bracing that don't require dwellings, but I guess that's talking to your engineers and just having the option of not having them in there, and that will greatly improve the performance of the wall, because we do need thicker walls really with insulation. So as soon as you start putting more and more timber in there, you lose that R value, like Simon was saying. So
good.
And we have the QR code on screen there, everyone. If you want to scan that, that'll give you access to the document that Richard was talking about from Oculus Engineering, Sean McIsaac. So feel free, get your phone out and scan that code.
And if you want the short version of that, the answer is actually no. Nogs are not required, and you can read that in NZS 3604 in section 8.5.4. So that is the wording which tells you that you do not need them. There are options. Good stuff. All right, thanks team. We are going to crack. Oh, go on. Yep.
The boundary of where nogs and dwangs comes in. I'm from Taranaki, and we always used to know them as dwangs growing up. So I think that it's probably around the Waikato somewhere that they start becoming nogs.
Okay, I thought it was a pure South Island
what are you trying
thing.
to say, Richard?
Yeah, point of
South Island and nog?
Great. All right, Simon, let's kick back to you. Let's go.
Thank you, John. Now, many of our buildings have steel members such as I-beams or RHSs in order to allow for greater spans. In the image, you can see there's one piece of steel which is being sneakily hidden away in the wall on the left-hand side of this image. And that's the one we're concerned about, because that can cause, first of all, poor thermal performance of the building. And the pieces on the right-hand side are okay because they're included within the thermal envelope of the building. But when we have a beam of steel sitting from the inside to the outside of the wall, effectively that is creating a thermal bridge, and that can very easily get cold, and we can expect to see condensation and later with that mold and things developing in that wall. We know that steel is more than 1,100 times more thermally conductive than the fluffy insulation in that wall space. So wherever you've got steel, try and keep it well insulated within the envelope of the building. Now, with the increase of insulation values in the ceiling, we can probably expect some more increases along the way, and it's likely to be the walls that are going to be considered next. When we expect that the NZS 3604 update within the next 12 months will likely default to 140 mm framing for the space it creates for the insulation. The FTMA feedback was when we were there earlier in the week that this will add significantly more cost as well as more for transport and manual handling. So 140 framing is 30% heavier than your 90 mm timber stud. Now, if you look at this picture, when you can see the stud line on the inside, it probably means that we can expect to have mold in that construction. Now, why is that? Lack of heating, probably lack of ventilation. Timber frame is colder than the plasterboard, so that's where the condensation occurs first, along with mold growth later. I would argue that changing from a 90mm frame to 140mm frame is unlikely to make a difference in this scenario. Why, you may ask? None of the conditions are changing. The insulation isn't a heater. Why is this important? Because the promises from MBIE were these changes will deliver warmer, drier, and healthier buildings. What were those changes? Increase in the number of climate zones, increase in the insulation requirements. Too big a promise, I think. Back to you for another poll, John.
All right, that's a really interesting thing to look at, that last slide, just realizing that the change in depth in the frame can't actually change the conditions, right? So, you know, you have 90mm of insulation in there or 140. If you don't heat, if you don't ventilate, the outcome will be the same. So there are some good challenges ahead with that, or same or similar maybe. Okay, so the poll question we have, again, this is a bit of a fun one, bit of a dig at some of the things that we do. So what is the dumbest thing we do? Answer one, too much timber in the wall. We've covered a bit of that in the presentation already. Second, is it a lack of ventilation? That's the dumbest thing we do. Is it a lack of insulation? Now that might be a combination of that first one, too much timber and not enough space for insulation, or it could just be a lack of insulation. Or finally, 6.6, is there too much insulation? Is that the dumbest thing we have decided to do for our buildings? So that poll is open, and remember, you need to submit your answer to that. As we do that, I'll just remind you also that we have an open Q&A panel in that chat, or just below that chat function. It should be on your screen. So please feel free to drop in questions, hard questions, easy questions are good too. And how are we going on that? So 70% voted, 71, that should do. Let's kick on. Right, team.
Oh, stop. Lack of ventilation.
Lack of ventilation, love it. All right, I'll leave it up to you guys to discuss.
What do you reckon, Catherine?
What do I reckon? I reckon there should be like a fourth option. I mean, the lack of ventilation, we're not going to cover that in our series, but it's definitely going to be referred to G4 throughout all of our presentations on this. Yep. And lack of ventilation is definitely a dumb thing to do or not to do.
That'd be true as well. I mean, we're generally talking to people that are looking to make their building more energy efficient, you know, increase insulation, make it more airtight so you don't lose as much energy out to the outside, keep the inside outside out. But I can see that, ventilation systems aren't really being designed in as much. You know, reliance on, I guess, windows for ventilation, while it's in the code. I mean, the code actually does say that you need a certain number of air changes even in your living spaces, so you can't reliably get that if you're just relying on windows. So yeah, I think lack of ventilation is probably the big one. You know, improving the ventilation requirements, sort of making systems more mandatory. Ventilation systems might be the next thing they look at. A good idea, I think.
I think in terms of like our 6.6 and the roof as well. I mean, do you really need that much when you're just kind of stacking a beanie upon a beanie upon a beanie on your head, you know? So yeah. I think going from the schedule method to the modeling method and figuring out, you know, where to put the right components. You know, you may need less in your roof, and you may find that you might gain a bit more in your building when you put better windows in, or
yeah, like they say, you know, the windows are always the weakest link. Even the best insulated window with a, you know, a thermal resistance of about R1 is still far less insulated technically than a you know, a sort of an okay wall. So I guess, yeah, improving your windows is going to have a massive effect, and using Echo or PHPP for your thermal modelling can sort of show that you're meeting the energy requirements, energy targets. So having really less, and more for less, really, isn't it?
Yeah, by 2030, right, we're going to have our shit sorted, if I can say that.
You're not allowed to say that publicly. Thank you,
Sorry.
Catherine. Catherine in Queenstown.
Date.
Maybe that's is that like nogs and dwangs? You keep
Oh,
that
yeah,
in the South Island.
yeah.
Hey, I'm interested too, and our discussion today is around B1. Now, I wrote this poll question, but the point there is that B1 doesn't sit on its own. You know, we just talked about ventilation. Well, that's G4. That relates really, really closely to E3 internal moisture that we will talk about. So these things, you know, we can't talk about them in isolation. And so that's why we're doing this, even though, yeah, again, our session is about B1. But the too much timber part, what we're not, and as Simon pointed out earlier, we're not making claims, we're not structural engineers. And that's the point, that we need to find out better ways of, you know, adequate structural performance. I think, Simon, you named it as all of that timber in the wall shown in the photos from Beacon Pathway were sufficient to hold up an elephant enclosure. Yeah, is there, you know, was there a need for that timber? If so, great, use it. But if there isn't, if it's just whatever reason, just, you know, 8 studs in a row, come on, there's got to be some other options that we've got there. All right, hey, thanks panel. We're going to kick in again. We are doing well for time, and again, just pop your questions into the questions function on screen, and let's keep going. Simon?
Awesome. Thank you, John. Thank you, panel. So we've talked a lot about some of the issues, but now we're going to have a look at some solutions that you can do to make a positive change. Now, having a look at this detail, we were really excited when we saw Build Magazine of February 2021, where brands actually talked about this. So if you have a look at this image on the right-hand side, we're starting off with our internal plasterboard lining. And as we start moving towards the left-hand side of this wall, you'll see that we've inserted some horizontal service cavity battens. Now, these are 45 by 45 timber battens, and inside of the space of these battens, we're going to do a couple of things. First thing we can do is we can run our services here. So we can use this as a dedicated space for both electrical as well as some plumbing. This allows you to keep it out of the main insulation layer. Secondly, we can go along and we can add another layer of insulation here. Now, the benefit of this is, first of all, if we were using a 90mm stud, we might have been limited to, say, around an R2. But if we're moving up to or actually a 2.8, I think you can get. Is that right, John? In a 90mm stud, what do you think the maximum insulation you'd get at the moment?
Yeah, 2.8 is probably the highest one that we can get, and it's all dependent on density and somewhat the product, but yeah.
Yeah. So by adding another layer in that, excuse me, in that 45mm, we could be able to get up easily up to an R4, which is going to make our walls perform much better. But the other benefit here is by having the insulation layer running in 2 directions. So we've got our vertical one between our studs, and we've got another layer running horizontally, which is crossing across the insulation. So what this means is that we're cutting out a great deal of the thermal bridging effect of the timber in this wall.
Simon,
next, as we move,
just on that, whose diagram is that?
This comes from brands, John.
Yep. And then they've also got their recently published one, which is the Skillion roof, which is a really similar layup of materials, including an air and vapor control layer towards the inside of the main frame. Great.
That's right, John. So moving on towards the left-hand side of this, you'll see that we have something called an air and a vapor control layer. Now, the purpose of this is twofold. First of all, and most importantly, this layer will control the movement of air and thus vapor from the warm inside of the building towards the colder outside of the building. We know that warm air will always try to move towards the cold side. That's a basic physics principle. So once that warm, moist air meets this layer, the layer will actually stop it from moving further and getting to the space of the wall that is below the dew point where we can get condensation to form. Many people might think that, oh, well, the plasterboard's sitting there doing this, but problem with the plasterboard is we often have plugs, switches, lights, etc. in this layer, which are stopping it from being a complete vapor or air control layer. So next we've got our insulation and our structural layer, and then on the outside we would have our either a flexible or a rigid air barrier, followed by a cavity and whatever cladding we've got in this wall space. Was there anything you'd like to add to that, John?
I think it's good. And just to point out, the 140 frame could be 90, could be 190, but that's a climate-driven decision, not a you must use 140 frame. And that's what we are hearing and seeing coming with the update with 3604, which is not, yeah, it's like the 6.6 right across the country. It's not a climate-driven decision. It's a rule-driven decision which needs to be argued.
What about cost, John? Do you think what would be the comparison between a 90 plus 45 versus a 140 frame?
Yeah, let's not go for meter rates, but we can go for lineal meter rates. So we know that 90 by 45 framing and 45 by 45 as shown here, sorry, not shown here, that's 140 framing. Let's go back a step. 90 by 45 and 45 by 45 is cheaper than 140 framing on its own. So those two combined, so from a lineal meter rate. So that's an interesting comparison to begin with. But when you do this layup in a wall, you end up with a higher performance with the same amount of space. And that's the key bit that we want to get to. You described it before. We've got, in this example, horizontal battens and vertical studs. Straight away, we don't have the same transfer of heat from inside to outside through that wall as we would if it was only a 140, or in this case, a 190.
Thank you, John. So there are also some other ideas here. We can look at something called external insulation. So having a look at these wall details in plan view, the better option is to put the insulation on the outside of the framing. And we could well call this a warm wall, much like we have a warm roof, where all the insulation is on the outside of the structure. That's the definition of a warm roof. The structure is warm. If we put the insulation outside of the wall structure, then the structure is warm in the wall. So if we have a look at figure 1 on the left-hand side, the outside is on the left. The blue line would be our cladding. Then we would have our battens. The insulation layer, the orange, is now continuous, and it is installed as a blanket on the outside. The green line could well be a rigid sheathing of some type, plywood, OSB, plasterboard, or fiber cement perhaps. Now the structural frame doesn't require the insulation to be between it. There's a strong possibility, I know that John has modeled this, where you can use less insulation for the same performance. And this makes a lot of sense if there's no framing breaking up the line of the insulation. This change in performance is even more noticeable in figure number 2, where we've got light gauge steel frame, where insulation would be severely degraded by the conductivity of the steel. So if the insulation is all on the outside, then that frame is kept warm. In fact, it's going to be the same temperature as the timber frame in figure 1. Well, that's if the insulation thickness was the same and everything else was equal. Moving across the right-hand side, if we look at figure 3, it's only slightly different this time, showing a mass timber wall, such as CLT or cross-laminated timber. There's no room for insulation in the structure. Insulation cannot go on the inside, it must go on the outside, and there we have another warm wall. So things are not all perfect yet. There are still some challenges that we need to work out. For example, if we have a look at slab edge insulation, so with the new H1 requirements, we're expecting to see some form of insulation installed on the edge of the slab. Now, when you've got the insulation on the edge of the slab, you want to try and line that up with the insulation in the wall. So this means moving the bottom plate out over the edge of the insulation. And this can affect the hold down bolts because they're now going to move towards the outer edge of the slab. So we need to consider these type of details. We know that Winston Wallboards are currently working on looking at these sort of details to try and incorporate high performance details into what they're doing. Another area where we often see issues is missing insulation due to the configuration of our corners. So the frames get delivered, stood up, connected, squared up, plumbed up, and braced. The wall underlay then goes on the outside, and it's then really difficult to access the insulation and put it into the corner, because now we have, if you look at the red block there on the left-hand side, we're not able to get the insulation in there. So we asked the frame and truss manufacturers to start discussing this, and hopefully we can get better corner design. Does it save them time and material? No. Does it make a better building for the occupants? Yes. California corners, as shown on the right-hand side, allow for more insulation to get into the corner while there's still plasterboard fixing points. So corners are also a geometrical thermal bridge. Perhaps you want to tell us a little bit about that, John?
Yeah, that's a term which is used in, I guess, in the design with the thermal, that's a confusing way to talk about it. Simply put, corners are a weaker element, even with the same amount of insulation. So even the California corner on the right-hand side is still a geometrical thermal bridge, and so there is still more heat loss going out through the corner than there is through the wall or through the main portion of the wall. And that's we could get into that in an entire additional seminar around geometrical thermal bridges, because they occur in multiple places around a building. So it's a weak area, so let's do the best that we can by insulating the best that we can.
Fantastic. Thank you, John. So there's some other ways of achieving this as well. If you have a look at the graphic on the left, the jib fix metal angle allows for less timber at the corners. You can find these details as well in the Passive House Design Guide. They offer you some options. Just have a look at the QR code. You can scan that and have access to that booklet. You can download it for free. You'll see they've shown an example of what it looks like. But just to point out, Pro Clima are really strong advocates of the German Certified Passive House Performance Standard, which is a really great option. But you can apply the suggestions we're talking about today to every build in order to prove all of your buildings and give us all better homes to live in at the end of the day. Now, coming towards the end of this presentation, bathrooms are really where everything comes together. We're piping water into our buildings, turning it into steam, and the structure of the building happens to have the lowest temperatures, as we've shown. And this is where condensation will form. This is already moving into the final part of the seminar series, E3 for internal moisture. The key today is to recognize that the issues showing in the image in the middle. In the bathroom, we create high levels of humidity. The image shown is from a house in Cheltenham Beach on the North Shore of Auckland. Here we've got nogs that may have been added for tapware. We may also have in-wall systems, nogs for cabinets, cables, etc., and not much space for putting insulation. And in this case, it's been really poorly installed, or perhaps the electrician was to blame for relocating the insulation. But getting back to the summary, the structure needs to be there. So that's B1 structure sorted. But the effects of internal and external moisture due to the design and materials, or lack thereof, triggers effects on durability. That's Coe's clause B2, which brings us back to the original question of stability and B1 structure. It's not all doom and gloom. There are options and answers for this challenging area of kitchen and bathroom walls, and we've recently published an article in EBOS, which is freely available. The QR code will get you directly to that article. We'd love your feedbacks. So what are the options here once again? Internal service cavities will help keep the surfaces out of the bulk insulation in the main wall framing. Secondly, by putting all the insulation on the outside might just result in even a better building. So have a look at that QR code. I'd like to finish off by pointing out that if you're an engineer on the webinar, you'll likely use a simulation tool for structural analysis and planning. Beauty of simulation is being able to optimize the structure, not maximize it. Likewise, none of these things we've just discussed needs to be guesswork. Simulation tools like the one on the screen, which is called WFI, Hygrothermal Analysis, allow designers, engineers, and building enclosure engineers to test and propose material layups and how they relate into any configuration to the local climate, considering wind, rain, and sun on the outside, and heat and moisture on the inside. This allows for optimization of the materials and to avoid poor combinations at the design stage. Simply put, the cost of simulation is always going to be cheaper than building it and seeing what happens. John, back to you.
Great stuff. All right. Thanks, Simon. Hey, we've got some great questions coming. Let's start with one of the hardest ones. Simon, this is going to be aimed at you or Richard or Catherine, so we'll see how we get on. So the question that's come in that I'd like to start with is, what happens if we have external RAB or an external sheathing layer with no internal vapor control? So that is quite a tough question and even a little bit political. So let's see how we're going to respond to this. I'll be judging your answers as much as our audience. So hopefully that's a really good way to start. The toughest question out of the lot, I think. Let's go.
Richard, I might put that over to you. What do you think?
I guess it's dependent on a lot of things. You know, what's going on inside the building. You know, more moisture sources, occupancy. You know, looking at WFI here on the screen, we take into account the internal moisture sources. If there's one person in the house, or 15 people, or if there's 5 spa pools or something. Also the what ventilation there is, how airtight the internal lining is. You know, a lot of moisture moves through air convection, not through vapor diffusion. So lots to think about there. What the climate on the outside is. You know, if it was a tropical climate maybe, and there was a constant inward heat and moisture flow, then having a really good airtight, weather-tight layer on the outside might take into account. It'll stop the moisture coming in. But if it's a constant cold climate, having no internal air vapor control layer on the inside might be quite high risk. So there's lots of things. I mean, this is all what can be sort of modelled in WFI. You know, it's good for sensitivity analysis. You can take layers in and out and change the thickness of insulation in different layers, and it will give you reliably a good idea of whether there's going to be a risk of mold growth, timber decay, corrosion and that sort of thing, 1, 5, 10 years down the track, and at which layer. So many factors, too much for our little brains to sort of take into account. Use a program like Woofy, more accurately assess what their risks are. I mean, we're always advocates for internal moisture control layers, because we've done a lot of research on them. Our models all show that layer. Our details show that layer. We've got confidence in that, and that's the best way to design with sort of moisture sensitive framing such as timber. But it doesn't always mean that they have to be used, because there's lots of other different things to take into account. So long way of saying, what have I said? Yeah.
Well, it's good. I'll summarize it. And it's actually
Yeah.
in Simon's last statement, which was around the simulation at design stage being cheaper than building it and then finding out that it is high risk or didn't work, or actually, is in the realm of failure. So the simulation, and I think maybe Catherine, you could talk about where people would go for that, because that's not us. We're not the rule makers on that. So maybe you could just make comment around Woofy, the simulation software itself.
Well, we do have a lot of people that we've trained in Woofy. We actually have Woofy trainings. Jesse takes those from Australia, and all our Woofy operators are on our website. So if you just go over to there, and it's also quite important to get a third-party operator, I feel, because Woofy can be kind of a little bit manipulated to the better outcome. So it's quite often to get another party to do that. And also, I just want to add on that, having the no internal vapor control layer, or having that on the outside, like so the RAB board or any external RAB has always been an air tightness layer on the cold side. So what we're wanting to do is put that vapor control layer on the inside, on the warm side. So there's been some issues around, warm air reaching that cold air barrier on the outside. So
yeah,
add
great.
that in there.
Yep. And so, Simon, I'll fire the last question at you around this then. We talk about an air and vapor control layer. We do have one of those products, but what are the other options in the market? Because we don't have the only one.
No. Certainly, there's a number of options now, John. So we see many different manufacturers, obviously in Europe, providing a number of solutions, and as well as you could literally use something like plywood with the taped joints, so ensuring that you've got a continuous layer on the inside of the insulation, similar to what Brands showed in their skillion roof design in Build magazine last month. Plywood can certainly be used as an air tightness layer, but as I say, there are other manufacturers as well bringing out products. So we're starting to see this category growing as there's a lot more interest in ensuring the performance of our structures.
Cool. All right. Hey, we better. So it's really interesting that question. It's a really important one, and the result of poor moisture control, what we're arguing is that will affect insulation, or we're coming to that in a few weeks, but it will then affect the B2 durability of our structure. We're coming to that in 2 weeks with Richard Hollard, who's going to present. But then that in turn affects the B1 structure, the meeting of requirements to keep a building standing up for an adequate period of time. So that's why that question is obviously relevant and useful. So let's go a different question, quite a different one. So the combined 90 by 45 R value. So if we do the 90 mil frame and an add up of the R value in 90 mil frame with the service cavity idea to the inside, if we just stick with 90 plus 45, what's our outcome of an R value in that wall? And maybe it's easier not to do or attempt a construction R value, because we'd have to do some pretty flash calculations to take into account the stud and the batten performance. But if we just look at the R value spacing there, what is that?
I guess
So
What,
John,
9
carry on, Kath.
Everybody wants to answer. Great, Catherine.
okay.
I was first. A 90 mil frame's generally about R.2, right? And then we've got 45 is
No,
around.
let's clarify that. Sorry, R2, not 0.2.
Oh,
R2.0.
2, sorry.
Yeah.
Yep.
I know what you mean.
I know, yeah. And
R20
then
in the States.
R20, yeah, R200. And then we've got what, 45 is 1.0 around about.
Yep. So I guess the point there is that R value on its own, and this is what we can't calculate on, off the top of my head, we can say that the 140 frame is going to have the same or similar amount of insulation as a 90 plus 45 roughly. So that's not enough. That is, we still will end up with a better wall because we're eliminating the thermal bridging. So maybe that's a calculation that somebody could do. It's probably already been done. It might be in a Beacon Pathway piece of research already as well. So still a good question. 90 plus 45, it's a better outcome with the same thickness overall of insulation.
Mm.
And John, that really comes down to thermal modeling, doesn't it? If you're going to run sort of a thermal modeling program, that is actually going to give you an increased performance value, because it's going to look at the air tightness of the building, it's going to look at the insulation in the walls, and it's going to work it out all together. And at the end of the day, I actually saw them talking about it on RNZ the other day, that the government is thinking about implementing some sort of an energy rating for houses soon, which I think is a long time coming, because that means when you buy a house, you've actually got an idea of what are going to be the long-term running costs of that.
Yep. Okay, hey, let's change to, again, we talked before about G4 ventilation wasn't going to be part of our seminar series, and that's almost true. We're going to be referencing it. So there's a question here which is asking how much a ventilation system will cost over the life of the home compared to using windows and doors for natural ventilation. So if I can summarize that question, it's actually not let's not start with the cost benefit analysis. Let's start with adequacy of windows and doors for natural ventilation, if that's okay. And we might get to the cost benefit part second to that if we've got time. Who wants to attack that? So great,
I've been doing a bit of,
okay, you got jumped. Okay, here we go.
Take away.
Who's going?
Yes, please.
I did a bit of a roadshow with Steve Altron recently, and we're talking about infiltration and ventilation through windows and doors, and that can really only work if you've got a window open on one side of the house and you've actually got a window open on the other side. You've got a pathway for that to go through, and it's actually not a calm day, so you do need pressure for ventilation to work in terms of cross ventilation. And you can actually put that into the PHPP as well to help with your ventilation statistics when you're doing your modeling. But generally, you really have to think about your openable windows and trying to get those air changes in.
I guess firstly look at why you're ventilating. Why do you need to ventilate? It's to remove contaminants, it's to remove moisture, it's to give us healthy air to breathe, I guess. And at the end of the day, us as humans, we're unreliable. We might forget to open the window one day when we've been doing it other days, and it's not so it's not consistent. I mean, a ventilation system, I guess, the set it and forget it type thing, it's running all the time. And also, windows are a bit unreliable because we do live differently these days. There's noises outside, there's security issues, we're living closer to each other. There's dust, there's bugs, there's all sorts of stuff which you can take into account and have clean filtered air all the time with a ventilation system. Whereas with windows, you're reliant on the weather conditions, having one open on both sides and all that sort of stuff. So it's just more reliable, and it's always going to be an additional cost at the start of the build versus not having a ventilation system, I guess. But the benefits here are something, it's hard to measure the benefits in terms of dollars, but it's in terms of health. And, you know, your kids going to school every day because they're healthy, going to work every day because you're healthy, and you become, I guess, more valuable members of society when you're healthy and breathing fresh air every day.
Yeah, and
Great.
Richard, often there's a concern about the ongoing cost of running the system. So I just recently installed a Stable Eltron into my home, and most of the time that system is using about 27 watts of electricity. That's about half the energy used by an old incandescent light bulb. And at maximum, when it's boosted, sucking out all the moist air out of my shower, it'll be using about 90 watts of electricity for half an hour. So it's really, really cost effective to run.
Cool. Hey, let's get back into a B1 specific question, and this is not a straightforward one. And there's some great comments and great questions coming, and there's a comment there about the 8 studs, and so I'm just recognizing it's a great comment. What we're not trying to do is say in that image that we had on screen with lots and lots of studs is that they weren't required for structure. We're saying let's work on better options. If that is required, then we need to do something different where we still need insulation, right? We need insulation in those portions of wall, so therefore we'd have to put insulation outside or do something different. So it's not about not needing structure. Again, it's not an engineering discussion as much. But let's get back to a B1 question. The question or request is, could you speak more on the B1 compliance for externally insulated walls, assuming this would all be specific design solution at this stage? Now, I don't know whether you guys want to jump into that. I'm happy to, because I've just had a bit of a think about it. But if somebody has commentary around that, that would be great, or I'm happy to.
You go, John.
You're probably the man to talk to about this, but my initial thought would be the structure's not changing, it's just the position of the insulation. So you're not actually affecting B1, but you'll be able to talk about it.
Yeah, and that's exactly right. So we were not changing the overall. So in the theory of this, if you like, it would still sit in 3604, or could still sit in 3604. But the external insulation is just being moved outside the wall structure. Now, where that happens, there is still a B1 requirement in the structural connection from the structure to the cladding, and that's a different gap than what it has been. So ultimately the rules don't change. We still need to have cladding connected. B1 structure says keep it attached, you know, keep things outside the building attached, keep the frame standing up, all of those things, keep windows attached. That's all B1 structure, structural connections. So will it be questioned going through council? Quite possibly. Sensibly, how is this going to be attached? You're showing something a bit different. We're not used to it. How will you attach? So great question in there. And it's an area that we see just again and again will come and be more and more popular with the external insulation. It just makes sense. All right, we had a question there about jib fix. I think we showed that in the wall. We are just about out of time. So what I'll do is I'll just there's a question there about the influence that Pro Clima has on the development of the New Zealand building codes. So yeah, we're part of some of the lobbying work in the background, but we're probably assisting other people to lobby on our behalf and on the behalf of other people in the industry. So that's a very short answer to a long question, but let's call it quits for us today. In 2 weeks, we will examine B2 durability, and Richard Hollard is running that presentation. We're going to be asking, one of the questions we'll ask is, are there too many Ds in the 4 Ds of, what are they? Deflection, drainage, drying, and durability. Are there too many Ds in that statement? And other weird stuff too in that presentation, but hopefully really extremely useful. Look, I'd like to thank you, our audience, for attending today, and also our panel, Richard and Catherine, and of course Simon, our presenter today. Nice work. Please feel free, you've got it on screen there, please feel free to get hold of our team for in-house presentations and on-site assistance. We cover the whole country, including Great Barrier Island. And on that note, thanks so much for attending, and we are bang on time. We'll see you next time.
See ya.
Thanks, everyone. Bye for now.